and welcome to Learn System View in 5 minutes. This is Tutorial 25 on the topic Phase Noise Modeling in Mixed Signal Systems. So we will start from where we left during the last video. However, in this tutorial, we'll talk about how to perform phase noise inclusion in our mixed signal system analysis. As you might understand, phase noise is a very important aspect and it can't be omitted when you're looking at mixed signal systems, especially for communications like 4G, 5G, basically which are OFDM based. So in this test bench, what I have is a couple of local oscillators. This local oscillator is without any phase noise, which I have enabled right now. And this local oscillator, where I have defined certain phase noise profile with frequency offset and the phase noise amplitude, which is a very simple and standard format. So we have attached a phase noise onto this local oscillator, and we have used this wire label based connections to make connections to our modulator. The second phase noise is inside this RF link, and if you open, we also have an up converter local oscillator where we have defined the frequency offset and the associated phase noise data. So we have a couple of places where we have defined phase noise because in real systems, any local oscillator will have a certain phase noise and we would like to model that. However, when we run the simulation, so I have activated no phase noise data in this local oscillator and we look at performance. So let's first look at the IF outputs at 70 megahertz. You can essentially see a clean signal without any phase noise effect. And we look at the RF output. Again, this is just the regular RF distortion where you can notice from the constellation there is no major impact, and then you have EVM around 2%, which is what we would expect. Now, if I disable this block and enable the source with phase noise, and we run the same analysis again, and let's look at the IF input, and this is 70 megahertz, you can notice the impact of the phase noise because constellation starts to rotate. And this is a classical signature of seeing the phase noise impact. And you can see the IF input going to the RF receiver has higher EVM, which is on an average around 5% or 4% here. And if you look at the RF output, we see similar distortion 4 to 5% in the range. And you can see the constellation having the phase noise impact as well as little bit of amplitude compression exhibited by our regular RF system. But the question is, how do we also take into account the phase noise inside this RF transmitter? So for data flow models, you don't need to do anything special because once you define it in the parameter, it comes out and you can analyze it. However, the noise generated inside the RF link model, we need to explicitly tell our mixed signal simulator to include that or to account for that noise. And that option is given to user to depending upon what he would like to do. For example, if we double click on RF link, we can enable this option, calculate phase noise. So let's go back to our original condition where we had a clean source going from the data flow domain, but we have enabled the phase noise from the LO inside the transmitter. And let's look at the performance here. So first, let's go back to our IF here. And in IF, you can definitely see it's a clean system, no phase noise coming from the digital system. However, if we look at the response here, we can see the phase noise caused by the RF transmitter local oscillator is giving a bad EVM, and we can see the corresponding impact. So whether you want to model the phase noise or the noise data from data flow going into RF and coming out, that's possible. Or you want to keep your baseband as clean design and you want to just study the impact of the RF phase noise, that can be done. Now, as a final run, I would enable both the phase noise. I have the phase noise in the data going from my digital section, as well as I have enabled the phase noise calculation from my RF block. So this is like representing a true nature of a complete actual mixed signal system application. So now what we see is the overall impact of the phase noise on our complete mixed signal system. So let me, just for clarity's sake, let me slow it down by artificially looking at pulse search. So this way, we ask the modulator to look for a sync pulse, but which is non-existent. It is only done just to slow down the measurement so that we can read the text here. So you can notice the EVM goes as bad as 13%, in worst cases, and this is clearly a sign that both our baseband as well as RF phase noise is accounted for. So that's all for this video. Hope you like the content presented here, and it will be very useful when you go into your mixed signal system analysis by incorporating all the real world distortion into the signals and do a true analysis rather than just do a pure mathematical analysis of your system, which necessarily doesn't give you the actual system performance matrix. Thanks a lot for watching.